Okay, so I thought today we will discuss the second assignment. Did any of you face any difficulties in the second assignment? Or did you all get the answers? Fine. The second one was, it's not the one that's due next week, obviously. The one that you submitted last week. Okay, let's discuss it anyhow. Okay. So the first problem was to make a trans impedance or a trans resistance amplifier. So if you want to convert a current to voltage, what is the simplest thing you can do? You have a current source and you want to convert it to a voltage. What's the simplest? Pass it through a resistor. Okay. What will be the voltage? I times R. Okay. If you make a circuit like this, what's the voltage? If you drive it with a current source, the same current source. What is the output voltage? Minus IR. So it's the same thing, except for the polarity. So why would you want to do something like this? Huh? What's that? Yeah. So the output impedance of this is very low, whereas this is equal to R itself. So that's one of the reasons. And the other reason you can work out. So this circuit is used very often, okay, and the context that you see very often is that of a photodiode amplifier, okay. So normally you have all signals appearing as, many signals appearing as voltage sources, but in a photodiode what happens is you have a reverse bias diode and then you shine light on it. Reverse bias diode, no current flows normally, but when you shine light, the current does flow, okay. So the characteristics of a diode, this is not the point of our discussion, but this is what happens. Characteristics of a diode are like this, okay. Now, when you reverse bias it, it moves, okay. So it acts like a source. So if this is I and this is V, in the first quadrant and in the third quadrant, it is dissipating power, right? Do you know this, or? So in the first and third quadrant, it will dissipate power. In the second and fourth, it will generate power. Okay. So you operate the photodiode so that it generates power when light is applied to it. Okay. And it looks very much like a current source or a high impedance source. And there will be the capacitance of the diode and any parasitic capacitance because of packaging and so on. So the model for a photodiode is this, and this is the reason why we are interested in the response of such a circuit. So what is the effect of this capacitance? So in this particular circuit, if you have an ideal op amp, the output is minus IR, okay. Now, let's say initially you don't have this capacitor. When I say ideal op amp, its unity gain frequency is infinity, okay. Then the output is, in fact, let me reverse the direction of the current source so that I even get rid of the minus sign. When I have an op amp of gain bandwidth product omega u, what is the output? If the op amp has a finite gain bandwidth product, what is the output of the trans impedance amplifier? I is not necessarily DC, okay. This is what I mean. What is it? What's that? No, the unity gain frequency is omega u. So the transfer function of the op amp is omega u by s. Okay. So it is IR by 1 plus s by omega u. Okay. So it has a low pass behavior and the unity gain frequency is omega u. Sorry, the 3 dB bandwidth is omega u. Okay. This is the 3 dB bandwidth in radians per second. Sorry, again I made this. Now you also add this capacitance. What happens to this response? So I have added the capacitance here. What happens to the response? What is the output? One by? Into? Oh, yeah. So we have to work it out. It is, it will be a second order expression. That's what we know. Okay. So we'll just work it out from scratch. If this is V0, what is the voltage here? What is the voltage at this point? Huh? V0 times S by omega u, right? V0 minus V0 divided by the gain of the integrator. Sorry, it is minus. Okay. So we just write Kirchhoff's law here and we get the output. So I will turn out to be let me call this CD. Okay. So V0 by I will be R divided by I think I called it RF in the assignment. I will change it everywhere. Okay. So we get a second order expression. So it has some natural frequency and some quality factor. What do we have to do to get no peaking in the response? So we have to make the quality factor equal to 1 over square root of 2. So that means that this is what we need to do. Okay. So this is the transfer function. What is the bandwidth? If you adjust this, what will be the 3 dB bandwidth? If the quality factor is 1 over square root of 2, what is the 3 dB bandwidth? So it is the natural frequency of this second order expression. Okay, and the natural frequency squared is omega u by CDRF. Okay. Is the 3 dB bandwidth, and from here we can see that is equal to omega u times square root of 2. Okay. So we actually get a larger bandwidth by introducing some peaking. We discussed this earlier also. So, without C, there is a first order roll off. Now, with C, you introduce extra phase lag in the feedback path. Now, as you introduce more and more extra phase lag, the circuit tends to ring more and more. Okay. So, essentially what you are trying to do is to introduce a tendency to ring just beyond the bandwidth without the capacitor. So, it goes something like this. Okay. But of course, if you overdo it, you will get something of this sort. Okay. That corresponds to Q more than 1 over square root of 2. So, you adjust it so that there is no peaking in the magnitude response and go with it. Okay. So, first of all, I mean, there are several ways of doing this, and I think some of you have done it that way also. So, you just started with some RF and then kept on adjusting it until you get no peaking. That is fine, but I think after going through a class like this, you should also know the theory so that you can calculate right away what the value of RF is. Now, if you assume this model with omega u being 2 pi times 100 megahertz, that is, if you use an ideal integrator model for the op amp and you use CD equals to 1 picofarad, you will get, I mean, you need to adjust the second pole so that the pole is at 200 megahertz. Okay. But that is if you have only one additional pole. In reality, the op amp model I gave has 2 additional poles. Okay. So, it already has a second pole at this. Now, you can try to, so the resulting expression is not the second order stuff that I showed, but really a third order expression. Now, again, you can do the same thing. You can calculate it for this. You will get RF to be, I think, about 800 ohms, and then you still see some peaking because of the extra pole. So, then you go on reducing it until it disappears. But we also discussed how to deal with the case when you have extra poles. Okay. So, when the poles are at high frequencies, we can combine the effect of multiple poles into a single pole. Okay. So, now we will have 2 poles. One is at P2 and the other one is at 1 over CD times RF. Okay. So, we can roughly say that the 2 are equivalent to a single pole P equivalent, where the reciprocal of P equivalent is the reciprocal of P2 plus CD RF. Okay. Essentially, the time constant of the equivalent pole is the sum of time constants of individual poles. So, if you do this, what happens? We want, what is the value of the equivalent pole we want to get a Butterworth response? 200 megahertz. So, we want PEQ to be 200 megahertz, and we know this already. This is at 400 megahertz. So, the feedback, the additional pole introduced in the feedback path should also be at 400 megahertz. Okay. One over CDRF should be 2 pi times 400 megahertz. So, this gives you RF to be 400 ohms. Actually, I think it comes out to be 398 or something, but we will say 400. Okay. So, again, many of you have got this empirically. I don't totally discourage empirical stuff, right? When you don't know theory, you should be willing to do it. I mean, you can't say that, oh, I don't know the theory, so I'm not going to design this amplifier. That's not a good approach to take. So, you can do it empirically, and also from that you will be able to discover how it behaves. The problem with empirical stuff is that you don't know the exact dependence on different things. You will not know the sensitivities. You will have to run a large number of simulations. Whereas the power of theory is that you, with one expression, you will get the whole answer. Of course, you will always reach a situation where the theory is too complicated, then you resort to empirical stuff. Okay. So, at least you should not stop yourself from designing or working because you didn't have knowledge of the theory. You can always experiment. Okay. So, I think most people have got this. Actually, I saw a few. I think the few people have got this one. So, if you look at the loop gain, this is at 100 megahertz. To get a Butterworth response, you will need a second pole at 200 megahertz. In this particular case, what we have will be 2 poles at 400 megahertz. So, 2 poles at 400 megahertz roughly behave the same way as a single pole at 200 megahertz. Okay. A single pole at 200 megahertz would have given you a maximally flat response. Now, this also gives you something similar. Okay. Now, the other thing I did, which is different from the question, is that I completely ignored the DC gain. I think some of you have taken that into account during analysis. Now, you can work out for yourself that it is quite inconsequential, especially for the value of DC gain I gave. I think I gave 1000 or something. Right? So, you can actually work it out, include the DC gain in the model. Instead of omega u by s, you use the this model. This model includes the DC gain. Okay. So, if you do this, you can figure out at what value of A0 the answers start deviating significantly, and the values of A0 you need for the answers to start deviating significantly is quite small. You can just experiment with it and try. Now, the reason I am saying this is the expressions just get more complicated if you do this without adding any value to the answers. Okay. Because the DC gain really matters only at low frequencies, at DC, unless the DC gain happens to be really small. Okay. So, most of the times you can safely do the analysis, all of this high frequency analysis regarding stability and so on, by ignoring the DC gain and assuming that it's an ideal integrator. But you should use the same unity gain frequency as was there. Okay. So, you assume a model with only the unity gain frequency, ignore the DC gain, set the DC gain to infinity, you will get more or less the same answer. So, this is what I also simulated before I set the question. I don't think there is anything complicated with the simulation. Once you have the op-amp model, the whole thing works quite easily, right? Is this visible? Yeah. So, the red stuff is, if you don't have the diode capacitance, it's a first order system. So, there is no overshoot or anything, and also here you see a first order behavior. I think the lines are rather thin, but I think it's still visible. Now, with the capacitor and the response being adjusted for maximal flatness, you get some ringing in the time domain, not too much, maybe about 5%. And then you see that the green curve the bandwidth of the green stuff is beyond the bandwidth of the red curve. Okay. So, yeah, another comment I almost forgot. So, some of you have plotted this frequency response from 1 hertz to some 10 gigahertz or something. Okay. So, why do you do that? A lot of you have done it. Why do you start the plot from 1 hertz? So, the plot looks like this. I think you have encountered this before, right? You are asked to use the area of the graph paper efficiently. But with 1 hertz here and 10 gigahertz here, it looks something like this. And there are very few points here. It may not even look like this. It may look like this. There is absolutely no information here. And then all of it is here. And then you can't see whether there is peaking in the frequency response or anything of the sort. In fact, some of you have taken, the way you have chosen the number of points it even looks like these are piecewise segments. So, if you don't choose enough points, you will not see peaking, obviously, right? If one of my, let's talk about ringing, because this shows ringing, but if one of my points was here and the next one was here, you will not see any ringing. You should choose the number of points and the axis limits judiciously, right? There is no need to plot from 1 hertz. Okay. So, you see where the information is and then make a judgment on what to plot. Similarly, for the y-axis, there is no reason to show everything from minus 300 to plus 300 dB. Okay. Any questions on this? Yeah. How it extends the bandwidth? So, beyond the analysis, obviously. So, the only thing I can say is that because of the phase lag in the feedback, it tends to go towards instability. Okay. Now, the frequency response is nothing but the response to the steady state response to sinusoid, okay, at different frequencies. Now, it tends to instability means the poles will start becoming complex and then probably start moving towards the imaginary axis. Now, if you have a set of poles like this, the natural response consists of oscillations at this frequency, right? So, the way what you are doing is you are trying to somehow, here you know that beyond this point the circuit tends to respond less and less to the sinusoids, okay. So, but if a circuit has poles like this, if a circuit has a tendency to ring, it's naturally providing some of these frequencies, okay. So, you make it ring slightly beyond this, okay, so that the combination of the circuit's response going down but combined with its tendency to ring will become flat. Of course, there is no guarantee that it will do that, meaning you can get a flat one because, for instance, you could by some weird circuit make it ring here. With L's and C's you could do that. Then probably you cannot do this. What will happen is you will get something like this. That is not useful, but in this case it turns out that the tendency to ring you introduce lies just beyond the bandwidth of the circuit without ringing. Okay, so it becomes flatter. So I think you have taken courses on filter design, right? So there also you do the same thing with when you have higher order filters, like you will have poles something like this. There will be something with a low Q that has a frequency response like this. The next one will have a tendency to ring but not too much somewhere here, and the next one will have tendency to ring greater tendency to ring. So the combined effect will be a flat one. Okay, or maybe something that undulates slightly and then falls out. Highest Q pole. Okay. Yeah, I mean it's the magnitude of the poles that decides the, yeah. Yeah, approximately, yeah, that's correct, yeah. Yeah. Yeah, that's correct. So in this case you will only get, because it's a second order system, you will get only 40 dB per decade. So if you had, let's say, 6 poles and then you adjusted for maximal flatness, you would get lot higher sharpness, meaning you will get, instead of this, you will get this. Is this the sharpness you are talking about? The sharpness of the attenuation? Yeah. So that is, that depends on the number of poles. Okay. So with 2 poles, if you try to increase the Q, it is going to give you a peaking in the frequency response. That we decide is not useful for an amplifier. Okay. Then the next part is, so basically here you see that there is a trade-off. Trade-off meaning once you have a diode with some capacitance, okay, your RF is limited to some extent. Okay, you can see that whatever, if you choose, let's say you choose a very high frequency op amp, it's not very useful because the feedback pole is introduced and the bandwidth you get will be omega u times. Okay, let's evaluate the gain bandwidth product for this. So you have some amplifier with a bandwidth omega u, and from this with proper adjustment of RF and so on, we got a bandwidth of omega u times square root of 2. Okay. So this is the characteristics of the op amp. This is the bandwidth. What is the gain? This is RF. Okay, let's ignore the second pole of the op amp in this analysis. Okay, let's assume that there is just the op amp is an ideal integrator and you have one pole in the feedback path. Okay. So what is gain times bandwidth? It is RF times omega u times square root of 2. But what is RF? You adjusted RF times CF. What is RF times CF? 1 by 2 omega u, isn't it? We adjusted that pole to be at twice the unity gain frequency. So, RF is okay, this is gain times does it make sense? Something is wrong in this. Oh yeah, here the gain has the units of transimpedance, so that's okay. Okay, so this is what we get. Sorry, not CD, CF. What I mean here is the capacitance of the diode. Okay. So this is what we get. So basically, given a diode, you can only get so much bandwidth, so much gain times bandwidth. Okay. So if you use a high frequency op amp, what happens is you will have to set the feedback pole to even higher frequencies. If you have given bandwidth to the op amp, given unity gain frequency of the op amp, you have to set the pole at twice the unity gain frequency. To do that, with a given diode capacitance, you have to reduce RF. Okay. So if you increase the bandwidth, you will have to decrease the transimpedance. Okay. But maybe that amount of gain is not enough for me. So how would I increase the gain? That was the motivation behind the second part of the question, that I want to make RF 10 times. Okay, in this case, I had a transimpedance of 400 ohms, DC trans resistance of 400 ohms. I want to make it 4 kilo ohms. So what happens if you do this? What happens to the circuit response if you do this? So it will peak quite a bit. How much does it peak? So you can see here, this is at about 4 and this is at about 8. So it peaks by about 6 dB or so. Okay. So the red curve here is on the left side is the time domain response and the right side is the frequency domain response. Shows quite a bit of peaking and also ringing. So it takes a long time to settle also. So if you put in a square wave, you will have to wait until here so that each time the square wave is settled and then it comes back. Okay. So one of which one? So that is if you want a saturating amplifier, but you may not want it, right? Yeah, but it won't saturate, right? I asked for, that's true. If you let the op amp saturate, that was only for modeling, but if you let the op amp saturate, clearly you will not see ringing, but the behavior will be nonlinear, right? So, but also I said that you should adjust the steps so that you get 1 volt output or something, isn't it? Whereas the limiting was 2 volts. So you should not see this. You should not see any limiting at all. Okay. No, this is because I used the same current step that I had used for 400 ohms. So, I mean, I used the 2.5 milliamp step and I didn't change it when I changed the trans resistance. So that's why, I mean, you should mentally scale this by a factor of 10. Okay. So, okay, it rings like mad. So, what do we do to fix this? Okay, so one of the things, I think many of you have got the idea that you should use a 0 to cancel the pole, or at least you should use a 0 to improve things, whether it's cancelling or doing something else, it's besides the point. So, if you plot the loop gain for this, the op amp's response will be like this, but the pole is somewhere within the, where is the pole? RF times CD? Huh? 40 megahertz, right? Because we previously adjusted it to be 400 megahertz. Now it is at 40. So it will do this, and clearly something like this is bordering on instability. Okay. So how do we introduce a 0? So that's the standard way. I think we sort of discussed this in class, that if you have too much phase lag, you can try to introduce a 0. So if you introduce a capacitor in parallel with RF, okay, that gives a 0 in the loop gain. What is the response of the feedback path from V0 to Vd? This is through the feedback path. What is this? Huh? This is what you get. Okay. So I think this is a pretty simple circuit. You can derive it afterwards. So what happens is that now the op amp's forward response is that of an ideal integrator. So the loop gain will look better than before. So this is the op amp response, and the pole is at a lower frequency than the 0. Okay. So you will get something like this, and between these two you get a higher rate of roll off, and then it comes back to this. And we discussed earlier that if the slope is 20 dB per decade, when it crosses 0 dB, it is a stable system. Okay. So this is what you want to do. Now of course you can place this anywhere. You can place this here, or you can move the whole thing left all the way to this side. So what happens in that case? Where would you choose to place this? So that will affect the bandwidth. Okay, that's what will happen. What is the bandwidth of the system assuming an ideal op amp? Assume that it's an ideal op amp, meaning infinite unity gain frequency. Huh? 1 by RFCF. Basically it goes through this parallel combination. So it's the bandwidth of this network. Okay. At low frequencies all of the current goes through RF. At high frequencies all of it goes through CF. The bandwidth is when equal currents go through RF and CF, and that is 1 over RF CF. So if you start pushing the 0 and the pole towards lower frequencies, the bandwidth will reduce, or that seems to be, with an ideal op amp you do the analysis and that seems to be the case. Okay. So there is a motivation for not pushing these things too much either. Okay. So how should we place this? How many of you got this answer, that you should place the 0? I thought there were more than this, but maybe you're too sleepy to even raise your hands. So how did you determine where to place the 0? So actually you evaluate the transfer function and you can still do the second order stuff to get no peaking. Okay. So again we do the full analysis to get the expression. So this is the current that is flowing through CD, okay, this part. And the current flowing through the feedback network is Okay. So I multiply the whole thing by RF and I get V naught by I to be RF divided by S square by omega u CD RF plus there will be two terms in the first order part. Okay. So I get essentially I get a second order expression without a zero. Does it make sense? Or should I be getting a zero here? The loop gain had a zero in it, right? Huh? Yeah. So that is looking at the Bode plot also you can decide that, well, you could have a pole and a zero very close to each other. You can't really say. Okay. So, I mean, you could have pole and zero close to each other and you can't say. Okay. So anyway, think about it. Why it doesn't show up in the closed loop? So, of course, once you calculate the transfer function and you know that you have to go through the same logic that you have to set quality factor to 1 over square root of 2, it is plain sailing. Quality factor is this is familiar to everyone, right? The way of normalizing the denominator to the standard form and finding quality factor easily. And this is 1 over square root of 2. Okay. So this gives 2 times CDRF by omega u. I'll square both sides to be equal to 1 over omega u square plus this is CD, right? Sorry. Yeah, that's correct. Yeah. That's there's a mistake in this, I think. Yeah. So there is a contribution to the second order term from the product of these two. So this is not CDRF, but CD plus CF RF. I knew that something had to cancel and it wasn't. Okay. So here we get this to be equal to 1 over omega u square plus 2 times CF RF by omega u plus CF RF squared. Okay. And this part cancels with this. Okay. So we can calculate quite easily what CFRF should be. CFRF is the reciprocal of the 0, right? So essentially the reciprocal of the 0 is now if I calculate everything in hertz, 1 over omega u is, or in megahertz, omega u is 100 megahertz. Okay. What is CDRF? It's 40 megahertz, 1 over 40 megahertz. So this is everything in megahertz. I have changed the units now. Okay. And this will come out to be, if I make this 100, this is 5. Okay. So this should be 4 by 100 square. So Z1 corresponds to 2 pi times 50 megahertz. Okay. So you place a pole at 50 megahertz and you get this maximally flat response. Okay. R naught before the, which one? Yeah. Yeah, we'll discuss that. Okay. So are you talking about something I did now or an alternative solution to this, right? Yeah, we can discuss that. Okay. So with 0 at 50 megahertz, you will get maximally flat response. And what will be the closed loop bandwidth here? What will be the closed loop bandwidth? It is the square root of this term, right? So the closed loop bandwidth will be square root of omega u by CD plus CF RF, and again I will calculate it in megahertz directly. So omega u is 100 and CD RF is 1 by 40 plus CF RF is 1 by 50, right? So what will this give you? This is this is correct? Yeah. So this is the, so something is wrong here. Is this the correct answer? Yeah. Okay. So the resulting closed loop bandwidth is 100 square root 2 by 3 megahertz. Okay. And also the other interesting thing you can see is that, let's see what the gain times bandwidth comes out to be. The DC gain is still RF and the bandwidth is omega u by CD plus CF times RF. Okay. And this is, and we saw that some time back. Okay, let me do this later. I will not spend too much time on this. But if you calculate the gain times bandwidth, you should get it to be greater than with the, at least you should get a sort of square root dependence, okay, not a linear dependence. It's not that the gain times bandwidth is a constant. That's what you should get. I will look at this afterwards. Okay. So if you do all these calculations, you will get the feedback capacitance to be about 0.8 picofarads. And you put that in the expression and you will get the, you put that in the simulation and you get the response to be something like this. It's the green curve here and you see that you cannot really see any peaking in the frequency response. Again, I am not sure how well visible it is. It's not the bottom purple curve but the one above that slightly. Okay. Now, if you look at the details of the pass band, there is very, very slight peaking. Okay. So you can see that this green curve comes and then rises up a little bit, but the scale is expanded greatly. So this corresponds to about 0.01 dB of peaking or something. Why does this happen? Huh? There is a op-amp has an additional pole also, which we totally ignored during the whole analysis. So if you increase the capacitance a little bit, it will go even lower. I mean, there is no peaking at all, but it's not really worth it because 0.01 dB peaking is usually okay. Okay. So this comes because of the extra pole that we ignored in the analysis. Okay. So basically you can calculate CF to be about 0.8 picofarads and then go on with the design. So this design now gives you a higher gain. It gives you 10 times higher gain. Okay. And the bandwidth is, so that was the point I was trying to make, that bandwidth is, this is about 140 by 3. So some 45 megahertz or something of the sort. Okay. Something under 50 megahertz. Whereas what was the original bandwidth? It was 100 times square root of 2. Okay. So if you look at it, without CF, to get maximal flatness, RF was 400 ohms and the resulting closed loop bandwidth was 141 megahertz. Now with CF, RF is 4 kilo ohms. The bandwidth is reduced, but only by a factor of 3. Okay, about 45 megahertz. It's really this bandwidth divided by 3. So you increase the gain by 10, but reduce the bandwidth by 3. This is because of choosing a different method of compensation. So that's what gives you this type of behavior. Okay. Of course, the bandwidth is smaller, but you get a much higher increase in gain. Okay, by going to a pole zero compensation and then still adjusting the zero position to get you a maximally flat response. Okay. Now some alternative solutions were also given. One of them was to use 400 ohms here. Okay. So this gives you no peaking and then follow it with a gain of 10 amplifier. What is there any issue with this? You did this. Yeah. So what are the problems with this, if there are any? So one is, of course, it's more expensive because you're using 2 op-amps in place of 1. But the bandwidth also goes down. What is the bandwidth of this stage? So this stage was 141 megahertz. What will be the bandwidth of this stage? Using the same op-amp. So let's say this is some R and this is 10R. What will be the bandwidth of this stage? 100 by 11. Okay. So that's about 9 point something megahertz. Okay. So this is completely irrelevant. It is basically 9 megahertz. That's the bandwidth. So the bandwidth goes down severely and it is more expensive. Actually, what you could have done is you could have increased R. That will give you some peaking and you reduce the gain here. So that peaking will get killed by the roll off of this. So that would be a better trade-off. I think overall you get a better bandwidth. But in general, this is a more expensive solution. And we haven't discussed it yet, but the input referred noise of this is a more noisy circuit than the other one. Okay. So in general, to get the best noise performance, you should amplify the signal to a high level in one shot. Okay. That will make sure that the signal is above noise. So this is kind of philosophically, you will see later through simulation also that this is true. Now if you keep the signal level small, each stage will go on adding noise. So the signal to noise ratio will go on reducing. So if you put the gain at the very end, you are losing out in terms of signal to noise. So you should put the gain, all of the gain up front, okay, at the very beginning to do very well in terms of noise. Okay. So that is the suboptimal thing. And one of you had done this, I don't know, I think this is what you suggested just now, to put a resistor here. Oh, you wanted to put it, okay. you wanted to put it like this. This I have not investigated. This will probably give a poor bandwidth. We can talk about it on Friday. Or does it give you the same thing? Yeah. Yeah. Yeah, that's correct. So let's discuss it in the next class in more detail. I'll also work on it. Yet another solution that was given was to do this. Okay. Does this work? Doesn't work. What do you think? It works, so you can fight him. Why do you say it doesn't work? Or what does it do? Huh? No, I mean the pole was already there, right? So what is this doing? It is reducing the loop gain. So it's actually doing both. It is reducing the loop gain and pushing the pole frequency outwards. Okay. So if you just look at this part of the circuit, what is the loop gain? If originally it was something, now it will get divided by this R ratio. So it will come down. Okay. So this will certainly get rid of the peaking. Whether it's desirable or not, we will see afterwards. Okay. Once you reduce the loop gain, it will get rid of the peaking. Meaning, once you reduce the unity gain frequency. Let's say your parasitic poles are at the same location. So let's say in fact our problem was not like this, right? So our problem was that this was the op amp and the pole was here. Okay. Now, if I push this pole to a point below unity gain, it will work. Okay. So this I can do by introducing an attenuation around the loop. Okay. So by reducing the loop gain. Now that is not the only thing this is doing. Where is the pole frequency? Let me call this Rx. Where is the pole? So let's go back to this plot. So the unity gain frequency of the op amp was at 100 megahertz and the pole, because of the feedback resistor and the capacitor, was at 40 megahertz. Okay. So if I just push it down, how much do I have to push it down by? Or where should the new unity gain frequency be to get no peaking? Forget whether this corresponds to the circuit I showed or not. How much should I push it down? Or where should the unity gain frequency be to get no peaking in the response? Huh? What's that? 10 megahertz. Why? 20 megahertz, right? Isn't it? If I have a parasitic pole at 2 times the unity gain frequency, I will get a Butterworth response. That's what I want. See, in the previous case, I had a ratio of 4 because I had 2 poles at 400 megahertz. Okay. The very first part of the problem, I have unity gain frequency at 100 and 2 poles at 400, which are equivalent to 1 pole at 200. Okay. So in this case, there is only 1 pole. So we don't worry about let's not worry about the extra pole at all. So what will be the bandwidth we get? Huh? 20 megahertz. Huh? 20 times root 2, right? Because you get a unity gain frequency, you get a Butterworth response, so you get a bandwidth more than this. 20 times root 2 is what you are going to get. Just like in the very first part, you got 100 times root 2. Okay? So this is 28 megahertz. So this bandwidth looks inferior compared to what we had. But where is really the pole? Does Rx have any effect on the pole? So here I am talking about the loop gain. Okay. So what is the loop gain in this case? I think we should stop at this point.